The DNN, Deep Neural Network, network in healthcare shown in the video integrated with LLM, large language models, for enhanced predictive analysis and medical decision-making in hospitals. At the end, DNN and LLM example. Pradeep K. Suri, author, researcher, and AI/ML architect. LLM and DNN integration in healthcare AI systems. The integration of deep neural networks, DNNs, with large language models, LLMs, offers a transformative approach to healthcare AI, enabling enhanced predictive analysis and medical decision-making. While DNNs efficiently process structured numerical data like vitals and lab results, LLMs handle unstructured text-based inputs such as doctors' notes and patient histories. This synergy improves diagnostic accuracy, facilitates personalized treatment plans, and optimizes medical imaging interpretation. AI-powered chatbots, driven by LLMs, can further assist in patient interactions and preliminary diagnoses, ensuring comprehensive and data-driven healthcare solutions. A Python-based approach demonstrates this integration by visualizing a multi-layered DNN and forecasting trends using bar and line charts. The visualization clarifies how LLMs convert textual medical data into structured inputs for DNN-based disease classification and risk prediction. Forecasting applications leverage LLMs to analyze historical trends and refine predictions. This combined AI framework paves the way for advanced applications such as AI-assisted diagnostics, hospital management systems, and intelligent healthcare assistants, revolutionizing patient care and medical research. How LLMs used with DNNs in healthcare. 1. Medical data processing. LLMs can interpret patient records, symptoms, and history and structure the data for deep learning models. Example, extracting clinical notes, prescriptions, and lab results to feed into the DNN. 2. AI-powered diagnosis and predictions. DNN processes numerical health data, vitals, lab test results, while LLMs process text-based inputs, doctor's notes, patient history. Example, combining structured data from DNN and unstructured data from LLM to improve diagnosis accuracy. 3. Intelligent healthcare chatbots. LLMs can interpret patient queries, summarize reports, and suggest medical actions based on DNN analysis. Example, AI-based virtual assistants for doctors and patients. 4. Personalized treatment plans. DNN provides risk scores and test results, while LLMs analyze treatment options based on medical literature. Example, recommending treatments based on similar patient cases. 5. Enhancing medical imaging interpretation. DNN models analyze X-rays, MRIs, and CT scans, while LLMs generate detailed medical reports based on DNN results. Example, AI-assisted radiology reporting. Python-based integration of LLM and DNN for a healthcare AI system. Explanation of the Python program in terms of LLM, large language models. The Python program is divided into 2 parts. 1. DNN, Deep Neural Network, diagram visualization. 2. Forecast with bar and line charts. Each part is essential for understanding how LLMs interact with structured data, numerical and text, in a deep learning framework. 1. DNN, Deep Neural Network, diagram visualization. Purpose. The program creates a visual representation of a deep neural network, DNN, with input, hidden, and output layers. This visualization is crucial for understanding LLM-assisted DNN models in healthcare AI applications. How it works. 1. Define the number of nodes in each layer. Input_nodes equals 9 rightward arrow 9 input features, example patient vitals, symptoms. hidden_layers equals 12, 10, 8, 6, 4, 2 rightward arrow multiple hidden layers with varying neurons. Output_nodes equals 10 rightward arrow 10 possible output predictions, example disease classification. 2 generate coordinates for nodes. The function generate_layer_coordinates, assigns, x, y, coordinates to neurons for plotting. Each layer is spaced equally along the x-axis, layer_spacing equals 250. Nodes in each layer are spaced on the y-axis, node_spacing equals 50. 3 create edges, connections between neurons. A loop connects each neuron in a layer to all neurons in the next layer, simulating a fully connected DNN. 4 plot DNN using Plotly. Edges, connections, are drawn using go.scatter, with gray lines. Nodes, neurons, are plotted as green circles with black borders. Layers are labeled sequentially. LLM integration with DNN visualization. LLMs interpret textual data from medical records and medical reports, to convert them into structured numerical data. This structured data becomes input for the DNN, which is trained to classify diseases, predict risks, or generate recommendations. The DNN architecture shown in the plot helps visualize how LLM-powered AI models process multi-layered transformations. Summary of LLM-enabled insights. Section How LLM helps. DNN visualization convert text-based medical reports into structured numerical data for deep learning models. Sales forecasting analyzes past trends, reports to refine predictions. This program demonstrates how LLMs work alongside DNNs in AI-driven decision-making systems. DNN and LLM as an example. DNN network, healthcare in the hospital. AI/ML model by Pradeep K. Suri. Explanation of the image, this is a prototype not for commercial use. Title. The image represents a deep neural network, DNN, model for healthcare in hospitals, developed by Pradeep K. Suri, focusing on patient test results and diagnostic imaging. 1. Structure of the neural network. This is a fully connected deep neural network, DNN, with multiple layers. Input layer, left side. 15 healthcare-related input parameters, features, that represent patient data. Examples: smoking status, medical history, symptoms, blood pressure, age, etc. Hidden layers, middle section. 10 hidden layers, each with 15 neurons. Neurons are represented as green dots, and the connections between them are shown as gray lines. These layers perform complex calculations to analyze patient data. Output layer, right side. 15 different healthcare-related outputs, which include diagnostic test results and final patient condition. Examples: ECG result, blood test result, MRI result, diagnosis, etc. 2. Explanation of inputs and outputs. Inputs, medical data collected from patients. These are 15 key health parameters used as inputs in the neural network. 1. Blood pressure. 2. Heart rate. 3. Temperature. 4. Oxygen level. 5. Glucose level. 6. Cholesterol. 7. BMI, body mass index. 8. Age. 9. Gender. 10. Medical history. 11. Symptoms. 12. Medications. 13. Allergies. 14. Previous diagnoses. 15. Smoking status. These parameters are analyzed using the deep learning model to generate predictions. Outputs, results from patient tests and diagnosis. The DNN model predicts 15 different healthcare-related results. 1. Diagnosis, overall medical diagnosis of the patient. 2. MRI result, magnetic resonance imaging scan analysis. 3. CT scan result, computed tomography scan result. 4. X-ray result, interpretation of X-ray scans. 5. Blood test result, report from laboratory blood tests. 6 urine test result, urine analysis results. 7 ECG result, electrocardiogram test results. 8 liver function test, liver enzyme and function analysis. 9 kidney function test, kidney health assessment. 10 thyroid test, thyroid hormone and function evaluation. 11 cancer markers, identification of cancer-related biomarkers. 12 allergy test, allergy response detection. 13 genetic testing, genomic and hereditary disease analysis. 14 viral infections, detection of viral infections. 15 final patient condition, the overall final assessment of the patient's health. 3 visualization details. Green dots represent neurons in the network. Gray lines indicate connections between neurons, showing how information flows from inputs to outputs. Dark background, the plot is optimized for a black theme, enhancing visibility. Annotations, labels on the left represent input parameters, while labels on the right represent output results. For purpose of the model. The model is designed to analyze patient medical history and current health conditions. It predicts possible diagnoses and test results based on input health parameters. Helps doctors automate medical decision-making using AI/ML. 5 practical use cases. Hospitals and clinics, automated patient diagnosis. Healthcare AI systems, smart medical assessments. Medical research, advanced disease detection. Predictive healthcare, early detection of critical conditions. Conclusion. This deep neural network, DNN, is a powerful AI model built for healthcare applications, integrating medical test results, patient symptoms, and historical data to predict a patient's condition accurately. Healthcare in Hospital Python Program Brief. The Deep Neural Network, DNN, is a powerful AI model built for healthcare applications, integrating medical test results, patient symptoms, and historical data to predict a patient's condition accurately. This Python program visualizes a deep neural network, DNN, designed for healthcare applications using Plotly. It defines a network with 15 input nodes representing medical parameters like blood pressure, heart rate, and symptoms, along with 10 hidden layers, each containing 15 nodes. The output layer consists of 15 nodes corresponding to various medical test results and diagnoses. The program calculates the spatial coordinates of each node and arranges them across multiple layers while maintaining uniform spacing. It then creates edges between nodes in consecutive layers, forming a fully connected network representation. The visualization is built using Plotly scatter function, where edges are represented as gray lines, and nodes are displayed as green markers with black outlines. Input and output labels are annotated next to the respective nodes for clarity. The entire diagram is displayed on a black background with white text to enhance readability. The final layout is adjusted for an optimal display, ensuring no grid lines or axis labels interfere with the visual representation. The output provides an intuitive understanding of the DNN structure used in a hospital setting for medical diagnostics and predictions. The Python program provides a deep neural network, DNN, visualization for healthcare applications in hospitals. Based on this program, the following reports and graphs can be generated. 1 Network Architecture Report. Details the number of input, hidden, and output layers. Shows the number of neurons per layer. Highlights how patient data flows through the network. 2 Medical Diagnosis and Prediction Graphs. DNN Structure Visualization, graph showing connections between input, hidden, and output layers. Feature Importance Graph, identifies which input parameters contribute most to the final medical diagnosis. Weight Distribution Graph, displays the impact of different nodes on final results. 3 Patient Health Condition Analysis. Vital sign trends, blood pressure, heart rate, oxygen levels, and glucose trends over time. Diagnosis Confidence Score, shows model confidence in different test results, MRI, X-ray, ECG, etc. Anomaly Detection Graphs, highlights abnormal health parameters. 4 Hospital Resource Utilization Reports. Test Recommendation Graph, predicts which medical tests a patient may need based on symptoms. Medical History versus Future Health Risks, Uses past diagnoses to predict future medical conditions. Efficiency of diagnostic tests, compares medical test accuracy and effectiveness. Vital sign trends for patient A. The top part of the image displays a line graph showcasing the trends of several vital signs over a period of 10 weeks. The vital signs shown are: blood pressure, systolic, represented by the red line. It shows a general upward trend, with some fluctuations. Blood pressure, diastolic, represented by the orange line. It also shows an upward trend, with fluctuations similar to the systolic pressure. Heart rate, represented by the green line. It remains relatively stable throughout the 10 weeks, with minimal fluctuations. Oxygen level, represented by the purple line. It also remains relatively stable, with minimal fluctuations. Diagnosis confidence scores. The bottom part of the image presents a bar graph displaying the confidence scores for different medical tests. The tests shown are: MRI, has the highest confidence score. X-ray, has a lower confidence score than MRI. CT scan, has a slightly lower confidence score than X-ray. ECG, has a slightly higher confidence score than X-ray. Blood test, has a slightly lower confidence score than ECG. Urine test, has a slightly lower confidence score than blood test. Liver test, has a slightly lower confidence score than urine test. Thyroid test, has the lowest confidence score. Overall, the image provides a snapshot of patient A's vital sign trends and the confidence levels associated with various medical tests. Thank you.